Now that we have understood the non-uniform axial loading, we will go ahead and solve a particular problem. So the problem that you have over here is that you have a bar which is hanging from the top. It is clamped at the top over here and it is being pulled by a force P. But unlike the problems which we looked at, this bar now has some amount of self weight, right? So previously we looked at in all the examples that had no particular self weight, and as you can tell that if this bar also has no self weight, then the deflection at the very end over here is simply going to PL divided by AE, right? Very, very flat example. But now you have that if you look at the question that you have to find the end deflection, that is the delta that you are trying to find. So this maybe I'll mark it as that is the delta that you have to find. If the bar is hanging under its own weight, so it has a self weight of its own, and this gamma is giving, which is the unit weight of material, and in addition to that it is also supporting this particular load P that is there, so which is the end load over here, right? Okay, so now how do we do this? So now we have this load which is sort of percolating from the top all the way to the bottom, right? So suppose if at a distance x we take a a section over here or an infinitesimally small element dx. Now if I have to maybe write the equilibrium equation for maybe just this particular part that is there, just to calculate the internal forces. So remember, you have to calculate the internal forces at every step now. Because it's not just the end load P, you have this self weight of the material which is also there. So if I take this particular section and maybe if I draw just a free body diagram of that particular part, what I essentially get is that, suppose this is my the bottom part where I have this load P which is acting over here, and I have this internal weight, that is the small self weight which is acting. So this self weight is nothing but your gamma, right? It is gamma times the area of cross section A and this particular length. So the total length of the bar is L and we have this x over here. So this particular length that you have is L minus x, right? So it is gamma A times L minus x, right? So to balancing all of this, you have this internal force, right, N over here. So N at x I'm calculating. So N of x is nothing but equals to gamma times A L minus x plus the load P, right? So these are all acting vertically down, so N of x is vertically up over here. Now another way to get N of x, since you guys love doing integrations, another way to get this quantity is how do we get it? The other way to get it is you take this infinitesimally small length dx over here and you essentially integrate from x to L. So another way to get your N of x, if I have to write in that way, will be integral from x to L, right? We have gamma A dx plus P, right? So if you do that, you will get gamma A times L minus x plus P, which is essentially equivalent to what you got over here, right? Same thing. Yeah. So now that we have the N of x, what we are trying to find is the end deflection delta, right? So let's write the formula of that one. So we have delta or the d delta for this small element dx. We calculate the d delta, then we integrate from the top to the bottom. So we have of our d of delta is simply going to be N of x dx divided by A times the area of cross section is the same. It is, this formula is equivalent to PL divided by AE. I am saying this formula over and over so it gets ingrained in your memory. It's PL divided by AE. So we have this d delta over here. So from this one, if we have to sort of calculate the delta, what you get is integral. Now we have to integrate from the top to the bottom, that is 0 to L N of x dx divided by A of E, right, where N of x is simply this guy over here. So if I have to write it further. So it is going to be your delta will be equal to, I can pull out the AE outside the integral because it's a constant. So I have 1 by AE integral of 0 to L gamma A times L minus X plus P, and this entire thing with dx over here. Right, so let me scroll a little down. So if I do the integration, what I will get is 1 by AE, the one which was outside the integral sign. If I do the integral, what I will get is your gamma A L square minus gamma A L square over 2 plus P times L. Right. So if I simplify this and pull this out of the parenthesis, what I will have is that for the first term, for this one, your A and A will cancel over here. So what we will get is gamma L square by 2E, right, plus PL divided by AE, right. So this is my eventual delta that I get. So this is my final answer that I have. But while I am marking this, I want you to introspect a bit. I want you to introspect and think that does it logically make sense? For instance, everything is a positive quantity. So yes, in addition to just having this load P over here, because you have a self weight, you will have some additional deflection, right? But suppose the bar was weightless. If the bar was weightless, so essentially, gamma is 0, you don't have a unit weight. This formula reduces to PL divided by AE, which is exactly what we had learned. If you have a weightless bar with a force P, the delta is PL divided by AE. So that chalks out, that makes sense over here. So if gamma was 0, so it was the delta is PL divided by AE. And now since you have a bar which has some amount of self weight, you're getting this additional deflection that is over there. Another important tip which I want to give you is that once you have the final answer, always check the units that you have. If you check the units of this one, it will be in the units of length, that is mm or inch or so on. And if you put this gamma and L square and things which cancel out, and if you put this E over here, you must ensure that or you can check that the unit of this quantity must also be mm or inch. So you have oranges compared to oranges, and not oranges and apples, that you have two dissimilar units which are sort of coming together and giving your final data. So these are the some of the other finer checks that you can do, right? So I hope this problem example was clear. So we had a bar which was hanging off its self weight and this load P, and we sort of took a small section, we found out what is the internal force that is there, and from that we calculated the overall deformation delta that was there.